Today I will be giving a brief summary of some of the scientific and practical lessons we've learned from the RAMP low-cost sensor network. These are the result of work by myself and my colleagues over the past 3 years, both at the Center for Atmospheric Particle Studies at Carnegie Mellon University, as well as at the French CNRS, funded by the ANR through the Make Our Planet Great Again project. The RAMP monitor, or Real-time Affordable Multi-Pollutant monitor, is a low-cost monitoring package developed jointly by the Center for Atmospheric Particle Studies at Carnegie Mellon University and by Sensevere, a Pittsburgh company which is now part of Sensit Technologies. The monitor, examples of which are shown in the picture here, is a self-contained package incorporating 5 internal gas sensors measuring a combination of carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, sulfur dioxide, ozone, and volatile organic compounds. It also has internal data storage and transmission capabilities using the cellular network, as well as a battery to allow for independent operation for several days. The unit can also be connected to external sensors measuring, among other things, particulate matter mass. Here I show 2 of the PM sensors we typically use, the MET1 Neighborhood Particulate Monitor, or NPM, and the Purple Area, or PPA unit here. As of 2018, we had 50 RAMP sites operating in the Pittsburgh area near CMU. For reference, over the same domain, the local regulatory monitoring agency, the Allegheny County Health Department, or ACHD, had 10 monitoring sites, only one of which measured all the pollutant species measured by each RAMP. We also co-located several RAMPs with the regulatory monitoring agency sites at 3 of their sites to calibrate and verify the performance of the RAMPs, which I'll discuss later. We've worked with colleagues to deploy RAMP sensors around the world with an emphasis on sub-Saharan Africa, where we currently have 20 RAMP monitors in operation in Niger, Ghana, Cote d'Ivoire, Rwanda, Kenya, and South Africa. While in Pittsburgh, our low-cost sensors supplemented the local regulatory monitors to increase the spatial density of data collection. In many sub-Saharan African countries, there are few or no regulatory monitors in operation, despite these being among the most highly polluted areas in the world according to remote sensing estimates. Low-cost sensors such as the RAMPs therefore represent an important first step towards continuous air quality monitoring in these areas. We deploy the RAMPs at a variety of different types of sites, from private homes and businesses to public facilities like schools and libraries. To facilitate this, we've developed a couple of techniques and hardware solutions. Wherever feasible, we attach the RAMP and all of its associated hardware, such as external sensors and power adapters, to a common metal plate. That plate can then be affixed to the structure by whatever method is most appropriate to the situation, some examples of which are shown in the figures here. Wherever possible, we prefer to mount on pre-existing structures. Fence posts and other freestanding poles are especially useful since they allow free airflow all the way around the unit. We also use solid structures like walls or buildings where necessary, and prefer to mount near corners where the airflow will be the least blocked by the structure itself. We also prefer temporary mounting methods like hose clamps or zip ties, as opposed to more permanent methods like nails or screws to minimize the potential for damage to the mounting structure, as well as to allow for easier relocation of the monitor when necessary. Where there are no suitable pre-existing structures, we can set up our own mounting poles, as shown in the figure on the left. We can also use a similar approach when we want to co-locate multiple sensors at a common site, where we use horizontally slotted struts to mount groups of up to 12 RAMPs on a single base. An example of this is shown on the right, along with several plate-mounted RAMPs attached to the railings. Once deployed in the field, RAMPs transmit their data to a server at regular intervals. This is where our data management process begins. Every morning, a series of automated programs read through the previous day's data files and load them into a local database. As part of this process, the raw text-based data reported by the RAMPs are reformatted into CSV files of the data for each RAMP and for each day. Simultaneously, there is some automated preliminary data quality assurance work done to remove nonsensical data, for example, negative relative humidity values or temperature values outside of a realistic range, as well as to filter out any data corrupted during the transmission, as shown in the examples on the left. Records are also made of gaps in the data as well as any unusual patterns in the data, such as prolonged constant values or extremely rapid variations. A second stage of processing is then done to take the full temporal resolution data, which represents one data point collected every few seconds, to a database average to a common time scale, for example, one data point every 15 minutes. At this resolution, the data from all the RAMPs for an entire year can be stored in a single database file for easy access. Of course, the original files are still preserved on the data server, and so the full resolution raw data is still available for future analysis if needed. The automatically generated reports cataloging suspected erroneous operations of the ramps are then verified by technicians to diagnose whether an error is actually occurring and determine what should be done to correct it. All this information is also logged, along with information such as where and when the ramps are deployed and what maintenance activities have been carried out. These records help us to keep track of and correct problems with the ramps, and are also recorded in machine-readable formats to work with other programs which analyze the ramp data. When we have the opportunity to co-locate one or more ramps together with reference-grade monitors, we can combine the data from the ramps together with the regulatory monitoring data to create a co-located dataset. We can use this dataset to develop calibration algorithms which translate the raw signals from the ramps into concentration estimates for the relevant pollutants. We've done this for the electrochemical gas sensors within the ramp, as well as for the external particulate matter mass sensors. For the gas sensors, we've tried a variety of different approaches for calibration. The figures shown here present the performance of the corrected ramp data in terms of the correlation coefficient R and coefficient of variation of the mean absolute error, or CVMAE, a precision metric. These metrics are assessed for the corrected ramp data as compared to the regulatory grade monitor data. I've organized each figure so that the lower left corner represents perfect model performance. The farther away from this corner you are, the worse the model performance is. The different colored markers depict the range in performance for different calibration algorithms, which vary from simple approaches like linear and quadratic regression to more sophisticated machine learning techniques like neural networks or random forests. I'm presenting a few different calibration models for the ozone and NO2 sensors here as an example. You can see that the performance is fairly similar across the different methods used, although there can be some slight differences. Also, the two figures on the left side denote performance from individualized models, where data from each ramp is used to build a calibration model which applies to that ramp alone. This is in contrast to the generalized models, shown in the figures on the right, where data from all ramps with the same mix of internal gas sensors are combined together and used to build one model, which is then applied to all the ramps which share the same mix of internal gas sensors. As we might expect, the generalized models are just a little bit less accurate than the individualized ones, since they are not attuned to the particular operational characteristics of each ramp. The story changes, however, when we move from the site at which the sensors were calibrated, which is what these figures here are showing, to a new deployment site, which is what these new figures on the right are showing. The hollow markers indicate the ramp's performance at the calibration site, while the filled markers are the performance at the new field deployment site. For individualized models, performance tends to drop sometimes somewhat substantially, as the ramp is responding slightly differently to the new environmental conditions and different pollutant mix at the new deployment site. The generalized models, on the other hand, show the same level of performance at the new site as they did where they were first calibrated. Since the generalized models are calibrated on data collected by multiple ramps, these models are more robust against the idiosyncrasies of individual ramps, and thus less sensitive to the small changes that ramps might undergo as they are moved to a new site where the environmental characteristics and the pollutant mix are different. For the particulate matter mass sensors, although the commercial PM sensor models we use estimate PM2.5 concentrations directly, we also perform an additional calibration based on performances assessed for these sensors compared to regulatory grade monitoring instruments for PM2.5. The correlation, mean absolute error, and bias values, as shown here, for the uncorrected or as reported data from these sensors are fairly poor, especially considering that the average concentrations in Pittsburgh are only about 10 micrograms per cubic meter. To improve upon this, we made use of a correction based on the hygroscopic growth of particles due to humidity, using assumed seasonally varying typical particle compositions to assess hygroscopicity. This correction factor, combined with additional linear adjustments to account for the difficulty in measuring very small particles using optical methods utilized by these low-cost sensors, tends to improve the performance of these low-cost sensors. For comparison, the red lines shown here indicate the performance assessed for federal equivalent methods versus federal regulatory methods assessed for the same period of time. Although the low-cost sensors are still not performing as well as these regulatory grade methods are, they are more comparable in general, with daily average errors being on the order of 2 to 3 micrograms per cubic meter PM2.5. Averaging several months of data together can reduce these errors even further to below 1 microgram per cubic meter for annual averages. With these calibration methods in place, we can use a database querying system to select ramp data collected at specific times and locations, using the information on the deployments of the ramps as recorded in the log information, and then apply appropriate calibration algorithms, as I described earlier, to get the best guess estimates of air quality from the ramp sensor data. This can be used for a number of different purposes. First, we can use this to help confirm or inform our diagnoses of possible errors with the ramps themselves. We could also use them to generate air quality reports to give to the hosts of the ramps to give them an idea of what their local air quality is. Finally, we can analyze spatial and temporal patterns in the data to do larger scale analysis. I want to briefly touch on some of the results we've gotten from analyzing the data from the ramps. On the final slide, I'll present some references to the papers in which these results are presented, in case anyone wants to look at further details on these results, but I'll give a brief summary of them now. For Pittsburgh, we've done analyses on the spatial and temporal extent of impacts of local pollution sources on the air quality in Pittsburgh. In particular, we've looked at the influence of the Clairton Coke Works plant to the south of the city, which we found can affect the air quality mainly in East Pittsburgh during periods where the wind comes from the south. We've also looked at environmental justice issues in Pittsburgh related to air quality using the ramp data for example, NO2 as shown here. Elsewhere, in Puerto Rico, in the aftermath of Hurricane Maria, we were able to deploy and operate several ramps while the local regulatory monitors were still out of commission due to power losses. These ramps gathered data which indicated the impact of diesel emergency generators on the air quality in the San Juan area, indicating possible exceedances of air quality standards related to SO2 during the operation of these emergency generators. In Rwanda, we used the high temporal resolution data from the ramps to assess the impact of a car-free Sunday policy in the capital city of Kigali, where we found there was a measurable drop in morning air pollution levels on days when this policy was in effect. Overall, I want to leave you with a couple of general recommendations based on our experiences. First, an adaptable deployment strategy featuring, as much as possible, self-contained and modular low-cost sensor systems allows us to take advantage of a variety of possible deployment locations for our sensors and facilitates the quick deployments and maintenance of the sensors. Second, having an automated system for data collection, processing, management, and querying will make utilizing the data easier. Having such a system in place before you even start collecting data is always ideal. Third, we found that despite the good site-specific performance of individualized calibration models, generalized models tend to be the most robust against changes in sensor characteristics and site pollution mixes, which happen over time as the sensors age and as the sensors are moved from one location to another. For new environments, such as new cities or countries, new calibration models should always be developed for the local conditions. Finally, with appropriate respect for and quantification of the uncertainties related to low-cost sensor data, they can be effectively used to collect spatially dense data in previously monitored areas or to extend data collection to areas where currently there are no routine air monitoring, such as in sub-Saharan Africa. Thank you.